Hello everyone. Thanks for joining us. So you should see on your screen my first slide and also a pointer in principle. So I hope it's okay. So okay, today's lecture is about second quantization, and so that's what I'm going to tell you about in the next 1 hour and a half and a bit more if we have questions. Well, first of all, before I start, if somebody asks me what kind of textbook would you recommend, well, there are many textbooks about second quantization. The reason why I picked up this one is because inside you will find basically quite a detailed review of quantum chemical methods that I will not really talk about today. But all these methods that enable you to calculate approximately many-body wave functions. I mean, all these methods that we use for molecules are explained in this book, and they all rely on the second quantization formalism. So, of course, there are 2 chapters at the beginning of the book where many things are explained, and I will use some of the notations, okay? But well, you can have a look if you want. You will find a lot in this textbook. Okay, so what's the program for today? Well, first of all, I thought that I had somehow to review some of the concepts that Vincent talked about last time. Some of them, in particular, the concept of atomic orbitals, molecular orbitals, and also spin orbitals, because I will need this later on. And finally, Slater determinants. I won't say much about that, but I need to be sure that we all understand each other in terms of notations in particular. And then we will really get into the second quantization stuff. So there are many things I'm going to tell you about, like what we call creation operators, annihilation operators, the concept of excitation operators, and how we write Hamiltonians, so ab initio Hamiltonians in second quantization. Okay, and we're going to spend lots of time on that. And finally, if I have time, and I hope I do, I will explain you why this is called actually second quantization. Why do we distinguish first from second? What's the difference? Where does this come from? And by doing so, I will actually have, I hope, the opportunity to tell you about some operators which are very useful to evaluate like the electronic density, which is the basic variable in density functional theory, but also the one electron reduced density matrix that you will hear about in a lecture later on. And if I have time, just some words about the green function, because I can also use the second quantization formalism to define many-body green functions. All right, so last time Vincent told you about atomic orbital basis sets. So basically, again, I want to review this rapidly, but just to be sure that you understand the notations. So I will start with a simple situation, just a single atom, okay? And so I assume that this atom is located at the center of my frame. Okay, I'm using Cartesian coordinates. And well, of course, I can just indicate the position of an electron with some position vector that I will just denote R in a bold font. So this is a collection of Cartesian coordinates for the electron, okay? And well, usually we use Gaussian functions to construct atomic orbitals, and this is essentially how they look like. So this is what you should see here. So, so this atomic orbital is a function of the 3 Cartesian coordinates. So you have here the Gaussian part, okay, that you recognize with this exponent that you have tabulated usually in basis set files in quantum chemistry codes, but this is usually black box for the user. And then in front of it, you have some product of X, Y, and Z coordinates, the Cartesian coordinates, to the power of some integers, okay? And so these integers depend on the kind of atomic orbital you consider. So for example, if you have an S orbital, it's of course spherical. So you just have a bare Gaussian orbital, okay? But if you have a p orbital, like the px, then you will have an x in front. If you have a d orbital, could be like a d, y, z orbital, for example. Then you have this product of y, z, and so on. So you can create like that a full basis of atomic orbitals based on Gaussian functions. All right, so of course now we are talking. So I didn't mention, but of course I'm quantum chemist, so I will start by talking about second quantization from the point of view of quantum chemistry. But on the way, at the end, of course, I will have a language which is maybe more adapted to solid state physics. So I hope that everyone will be happy at the end of this lecture. Okay, but now I'm really adopting the quantum chemistry point of view to start with. So before, of course, my atom, my single atom was in the center of the frame, but obviously when I have a molecule, this will not happen all the time. So for example, if I have just two identical atoms located at two different positions, so this first position that is located with the vector RA, okay, and another atom at position RB, then I need, of course, to create an atomic orbital basis. So how do I do that? Well, from the atomic orbital I introduced previously, the only thing I have to do is basically to replace the coordinates R. I have to shift them by the coordinates of the nuclei. Okay, so this is how I can actually center somehow the atomic orbitals on each nuclei. So with a single atomic orbital, I can center either on the first nucleus, that is at position RA, or I can also center it at position RB, okay? And this is how basically I create a basis set. So the purpose is somehow to pave space with these atomic orbitals, okay? So, and to be very clear about what I mean by that, if, for example, you have a px orbital that you want to center on RA here, you see, well, as I say, you just replace x, y, and z by x minus xa, y minus ya, and z minus za. And that's how it works, basically. So this is how we generate a basis set of atomic orbitals, okay? Yeah, at least in quantum chemistry. So, okay, why do I tell you about this again? Well, something you should remember is that, and this was mentioned by Vincent last week, these atomic orbitals are not orthogonal because they actually have an overlap. So if you evaluate the inner product of two atomic orbitals, well, you integrate over space the product of the two orbitals, and they will definitely overlap. It's clear if you consider an s orbital, you have two Gaussians, simple Gaussians overlapping. So you don't get zero, okay? So the atomic orbital basis we are using is not an orthonormal basis, okay? And when we will move on to molecular orbitals, that will be something different. And this is important to know this because this will have an impact on the way we write things in what I will call later on second quantization. So we usually don't write second quantization in the atomic orbital basis. We use molecular orbital basis instead, okay? So how does it work? Well, in the simplest case where you would have like two atomic orbitals, so this chi A and chi B centered on each atom here, you can construct a molecular orbital just by taking a linear combination of these atomic orbitals, okay? So I just denote that phi p, where p is a label, so you have to label your different molecular orbitals. Could be a bonding, an anti-bonding, or it may refer to the HOMO or the LUMO, so you're familiar with that when you solve, for example, the Hartree-Fock equations. So it's just one of these molecular orbitals. And as I wrote here, it's just a linear combination of the atomic orbitals. And so these coefficients that you have to evaluate, so Vincent explained, for example, in Hartree-Fock theory, how to do that. So these coefficients are what we usually call in chemistry the CMO, so the coefficient of the molecular orbitals, okay? The MO coefficients, okay? Yeah, and when you do this, so this is a general notation. Now, if you consider any molecule, okay, your molecular orbital will always be expanded in the non-orthonormal basis of atomic orbitals. But nevertheless, that's a good thing. Once you have generated these molecular orbitals, they will actually be orthonormal, okay? So this is important. So when you pick up two different molecular orbitals, and you evaluate their inner product. So now you basically integrate over space the product of the two orbitals. So now I'm using real algebra, okay? So I'm in non-relativistic theory. Well, basically, so if P is equal to Q, you will get 1 because your molecular orbital is normalized. And if P differs from Q, you will get 0, okay? Which I simply denote here as delta PQ. So this Kronecker delta that I will use later on. So in summary, the atomic orbital basis is not orthonormal, but the molecular orbital basis is orthonormal. And when we will write down things in second quantization, in everything I'm going to do, and this is the standard way of doing things, I will always write in the basis of the molecular orbitals, okay? And that basis, I repeat, is orthonormal. So that's something to remember. All right. So is that over? No, not exactly, because when you create a molecular orbital and you want to occupy it with an electron, as you know, the electron has an additional degree of freedom, which is the spin, okay? And so more specifically, it's the projection of the Z component of its spin angular momentum, okay? Which can be either up or down. So in chemistry, we just call it alpha or beta. So you have two spin states. So if you want to have a full description of the one electron state, so to say, so the orbital itself, it's not sufficient. You have also to mention the spin, okay? So this is why I have these two pictures. Either the electron has a spin up or it has a spin down, all right? So once you've done this, so you specify what is the spin of what I will call a spin orbital, because I mentioned the orbital and the spin. What you get is a wave function, so a one electron wave function, which is a function, so not only on the space coordinates R, but also on the spin. So, and I denote this spin variable, I just write it sigma. So if, for example, your electron occupy a spin orbital with a spin up or alpha. So if sigma is equal to alpha, you recover your orbital, phi p, okay? And if sigma is not equal to alpha, you get 0, which is a way to say my electron has a spin up. So this is written again, thanks to this delta Kronecker function here. And so I have the two scenarios, spin up or spin down, okay? When I write things that way, you notice I use the same orbital, whether the electron is spin up or spin down, but it was mentioned last week by Vincent that you could actually use different orbitals for spin up and spin down. And this is what is referred to as unrestricted formalism. So it's used either in Hartree-Fock theory or in density functional theory, okay? So in the rest of this presentation, it doesn't matter actually if I'm considering a restricted or unrestricted formalism. So so it should cover all possible cases. So if I summarize the notations, and that's why I spent some time on that, just to be sure we understand each other. So now my spin orbital, which fully describes the quantum state of a single electron. So my spin orbital has a variable x. I do not just x in bold form here. So that variable is what? Well, first the position, like an orbital, but in addition, there is the degrees, the spin degree of freedom, okay, sigma, which can be either alpha or beta. So these two coordinates, space coordinates and spin coordinates, are just gathered into a single variable that I will denote x in the following. And this is a common notation, okay? So, so which means now that if you want to specify what the spin orbital is, you should indicate the orbital. So this is what I do now with this index P, but you should also mention what is the spin associated to that orbital. So is it alpha or beta? So here I just denoted tau. And rather than writing both spin the orbital label and the spin, it's much more convenient just to write this as a single index. And this is exactly what I'm doing. So the capital P here means that you refer to an orbital index and a spin index. okay? So basically, in summary, now every time I will talk about the one electron state, I will describe it like that. So, and that's going to be my spin orbital, okay? And the index P refers, so P P uppercase, capital letter, refers to a given spin orbital, okay? So this is just for the notation. And every time you will see on my slides, this notation like integration over X, this just means that you integrate over space, but you also do a summation over spin, okay? But I will not use this heavier notation anymore. So basically X bold here is my variable. Everything is included inside, okay? So for example, if you evaluate the inner product between two molecular spin orbitals. So you see now I'm having these labels P and Q uppercase, so which means that I'm really talking about spin orbitals. So this is how I would evaluate this inner product. And again, because I started with a basis of orthonormal orbitals, my spin orbitals will remain orthonormal. And this is important. This will have an impact you will see later on when we're going to start talking about the second quantization. So now in summary, we work with the basis of spin orbitals because we included the spin into the theory, and that basis is orthonormal. All right. So that's essentially the point about all this review of what Vincent talked about. By the way, I forgot. So last week, Vincent called this sigma omega, okay? But this is the same variable. This is what I mean here. So I'm also keeping an eye on the chat box. So if you want to ask questions, I mean, I'm going to answer them, okay? So do not hesitate to interrupt me if you have any questions. Okay, so so now we can, now that we have these notations, we can actually have some fun and construct many-body wave functions, okay? So, so how to do this? Well, the simplest thing, because we have, let's say you run your Rutherford calculation and you have several spin orbitals at hand. So what you can actually do is just put your electrons into these spin orbitals, okay, and create like that 2 electrons. So if you have 2 electrons, you will create a 2 electron wave function. So this is what I'm showing here. So typically, if you would like to assign, let's say, the first electron to this spin orbital phi p and the second one to the spin orbital phi q, the question is, how do you write the many-body wave function like this? So the simplest thing you can do is just, let's say, take the first spin orbital and you evaluate it at the position of the first electron, okay, position and spin, and then check the other spin orbital and now put inside the coordinates of the second electron, okay? So this is something that was already mentioned by Vincent last week, and this is what we call the Hartree product, all right? So this is really the simplest thing you could do. And you notice that if I do that, I basically distinguish electron 1 from electron 2, okay? And so we'll come back to that. What's the problem? The problem is if you proceed that way, it means that if you consider the scenario where actually electron 1 and electron 2 occupy exactly the same spin orbital, okay? So you would take this formula and replace then just P by Q. You get this product and it's not 0. So you get the non-zero result. So you have a wave function, okay? That is, seems to exist, okay? Well, the only problem with that is that basically, physically, this is completely wrong because if you consider that this wave function exists and has some physical meaning, it means that you violates the Pauli principle, okay? So this is prohibited. So this wave function should not exist in principle, okay? So it means that this is not the right way to do things, okay? So what's the problem? The problem is that I distinguished electron 1 from electron 2. And of course, there's no reason to do that because experimentally I cannot do that, okay? So when I construct the many-body wave function, I should actually be able to integrate or take into account the fact that actually what I call electron 1 could actually be also electron 2. So, and that's what I'm showing now in this, with this drawing here, is in fact, if I want to say that my electrons cannot be distinguished, I should actually consider the possibility to have like either this situation, but also the reverse situation where I would change the labels of the electrons. So in that case, electron 1 would occupy the spin orbital phi q, and electron 2 would occupy the spin orbital phi p. Okay, which means that if I do that, I don't need to distinguish anymore electron 1 from electron 2. So I would basically write simply this drawing, okay? So how do you translate that with a formula? Well, you need to take linear combinations of the different Hartree products that I talked about. So this is what I'm doing here, okay? And so this corresponds to this first scenario here, okay? And the other contribution, it's the other way around, so that corresponds to this scenario. And of course, now what I did is I put this minus sign in red because, of course, you may wonder why you didn't actually use plus, for example, okay? Why minus? So, well, we'll see that in a minute, but if you actually decide to use a minus sign, well, basically, you can rewrite this wave function, this 2-electron wave function, exactly like a Slater a determinant. Okay, this is what we call the Slater determinant that was introduced last week by Vincent. Okay, so the name Slater determinant comes from that. So this is the way we think we should write, for example, 2-electron wave functions. So why do we do that? Why the minus sign that actually gives you this determinant? Well, it's because now, if you reconsider the scenario where you would actually put 2 electrons in the same spin orbital, okay? Well, thanks to this minus sign here, if you replace P by Q, so basically you write P equal Q in this expression here, you get 0. So what does it mean? It means that now, with this Slater determinant, the Pauli principle is fulfilled, because it means that this wave function, where 2 electrons would occupy exactly the same spin orbital, disappears automatically. Okay, so which is the reason why we decided to use this sign. So this minus sign here is basically a mathematical translation of the fact that electrons are fermionic particles, so they cannot occupy the same quantum state. So another consequence of this minus sign here that was introduced is that if you decide to actually change the label of P and Q spin orbital, so what does it mean? So if you, for example, you look here at the first expression, the Slater determinant, you notice I started by assigning the spin orbital P to the first electron because I wrote X1 here. And then I have assigned the second spin orbital Q to the second electron, okay? But I could do it the other way around. So this is what I decide here. I say, okay, now I'm gonna basically assign the first electron to spin orbital Q and the second electron to spin orbital P, which means that I swap the indices P and Q. So if I do that, what happens? Well, not much actually. The only thing that happens is that I need to put a minus sign in front of the wave function, and that's it. Okay. So from a mathematical point of view, you would say that these two wave functions are essentially identical. Okay, they differ only by a sign minus, which has no impact at all when you evaluate any observable or you investigate any particle. So what does it mean? Well, it means basically that you cannot distinguish your electrons. Okay, so. And we usually say that your wave function is anti-symmetric. That's the idea, okay? So in summary, you do not distinguish, like if you start occupying the spin orbital P and then Q, or if you do it the other way around. The information contained in the wave function is exactly the same, okay? Okay, so what I just said now is very important because this is actually the motivation for using another mathematical language, another representation, something simpler that is more convenient to use when you try to calculate many-body wave function. And this is what second quantization is actually about. And this is what we're going to talk about now. Okay? So I don't know if there's any question about the first quantization thing. So everything I told you about, that basically Vincent mentioned last week, this is what we call usually first quantization, okay? And you will understand later on why, but this is the standard formulation that we teach to students, okay? Before we tell them about second quantization. So if there are no questions, I will move on to the second quantization thing. Now we get into, yeah, seems like. Okay, so basically what you see on the slide here, on the left-hand side, is the formula for a Slater determinant. And this is only for 2 electrons, okay? So if we had 3 electrons, 4 electrons, and so on, or a Slater determinant would be bigger and bigger, and it becomes even more ugly, okay? You have lots of terms. And when you think about it, it's a bit strange because the information that it contains, what it really means is quite simple. The information, as I told you, is, well, 1 electron occupies the spin orbital P, and another electron occupies the spin orbital Q, and that's it, okay? But if when we have to write the wave function, it means that we have to consider all possible permutations between electrons to be sure that the wave function is anti-symmetrized. But, I mean, all in all, the information it contains is simple. So the way we write it in first quantization looks a bit complicated, but the information is quite simple, okay? So what second quantization offers is just another way to write in the simplest way, in a more compact way, and also in a very convenient way when you want to do any calculation, this information, okay? So, what you have to understand is that second quantization is all about another way to represent things. So the information will essentially be the same. So this is what I mean by the information, okay? Now in first quantization, as I said, you write it like that. And in second quantization, what I will call second quantization, well, now you write it like this. So the purpose of what we're gonna do now in the next hour is to actually understand what this notation means, okay? But this is typically, so if you see this in a textbook or in a paper, this is exactly the second quantization way of denoting things. So even if you don't understand this notation, and there's no problem, that's probably why you're attending this lecture, the only thing you already notice is that the information you care about appears very clearly, P and Q, which are exactly the 2 spin orbitals that are occupied in your Slater determinant. And that's the only thing you care about, okay? So this is why it's much more compact than this, and it will become even more convenient when you will have, of course, more than 2 electrons, which is very common in chemistry and in condensed matter physics, obviously. Okay, so now what I'm going to do is I'm going to try to decipher this notation, and we'll do it step by step. So just some warnings before I start. So I do not pretend giving rigorous proofs of anything. I think I prefer to be quite intuitive, okay? So we're gonna play with different concepts, operators, and so on. But my idea is that at the end of this lecture, you should understand how the thing works, and ideally you should be able to use it, okay? This is really what matters. So I'm not giving any rigorous proofs, but let's just try to be intuitive, as I said. Okay, so I told you just on the previous slide that this is how we denote Slater determinants in second quantization. So now we need to understand exactly what that means, okay? So first of all, when you see this kind of notation, you should always, so there are things maybe you recognize. Well, first of all, you see we have the direct notation. There is this cat. So this state here is a quantum state, which is called vac. That stands for vacuum. So I'll come back to that in a minute. And then you have these 2 objects here with a hat, which means that they are actually quantum operators. Okay. So when you have this kind of a notation, you should always read it from right to left. So this is how you can understand what's happening, okay? And this is what we're going to do now, and then we'll try to understand exactly what this means. Okay, so first, if I read from right to left, the first thing I meet is this ket, which is a quantum state, and it's called vac because it corresponds to what we call in second quantization the vacuum state. This is super important because this is our starting point in this formalism, okay? So what is that? Well, first of all, you should be very careful. This is not the zero vector in the space of quantum states, so the electrons, which means that its norm is not zero. So the vacuum, I repeat, is not a zero vector. The vacuum is a quantum state, okay, which just means that there are no electrons at all, okay? And this is a quantum state by itself. So you may know that the vacuum has some very funny properties in physics. So the vacuum is not zero, okay? It is a quantum state like any other quantum state, okay? So this is what I'm writing here. So you should be very careful. In some textbooks, it's denoted as zero, but it's too dangerous, I think, to do that. So this is why I prefer the notation vac, so that there is no ambiguity, okay? All right, so by the way, when I talk about quantum states here, so if you consider the Hilbert space, so the space of all the possible quantum states, and the vacuum is one of them, okay? So the ensemble, I mean, the collection of all possible quantum states, which includes here no electrons, this corresponds to the vacuum. You could also have one electron, but you could also have two, three. So you consider all possible states, and the number of electrons can actually vary. And so this is an infinite dimension space, and this is what we call the Fock space, okay? So so our playground in second quantization is the Fock space when we can afford having no electrons, 1, 2, 3, 4, and whatever you want, okay? So this is really our playground. So it's quite cool because it means that we can, in principle, tackle any electronic structure problem, okay, at least formally. All right, so, and the vacuum is one element of it. It's one of the vector, but it's not the zero vector. Okay. Okay. Then what happens? So in front of the vacuum, we have this quantum operator here. So if I read it, and we'll come back to this, it will. So we call it AQ dagger. So this is this symbol here is a dagger, which means a dagger means poignard in French for the French-speaking students. Okay, because it looks like a dagger. Maybe you know the Chinese movie, The Flying Daggers. And okay, so we read it like AQ dagger. We'll see later on what that means, okay? But anyway, this is really a quantum operator that acts on the vacuum, okay? And we call that the creation operator. Okay? So this is one of the key ingredients in second quantization. So why is it called like that? Because its job is to actually create an electron and put that electron into the spin orbital phi q. So you see the index q here, the capital letter that I'm using to refer to a specific spin orbital is very important because this is exactly this index that I put here as a subscript when I'm writing AQ dagger. So AQ dagger means that I create an electron. So I start from the vacuum, and when this operator acts on the vacuum, you create a first electron. Okay. And then there is another operator just for, so we already created an electron, and then comes another creation operator, but now the label is P. So you create an electron, and now you put this additional electron into the spin orbital phi P. Okay. So it's really exactly what we're talking about, because I remind you that initially we were discussing about a Slater determinant written in first quantization, where one electron could occupy the spin orbital phi p, and the other electron was occupying the spin orbital phi q. So basically, this is a kind of compact way of writing things in terms of operators, but all in all, the information is exactly the same. Okay. So just some comments. In this notation here in second quantization, so you can consider the fact that I put the two operators, so AP dagger and AQ dagger close to each other, this is usually what we just call a product. Okay, we make a product of operators. But it has to be clear that what we mean by that is that we actually compose. So composition means that when I have this product, it means that, let's say I start, as I said, from the vacuum. I still read from right to left, okay? So, okay. So basically I have the vacuum here. I created my first electron and put it in spin orbital Q, and then second operator. Now on that basis, I'm creating another electron, okay? So this is exactly, so we never write things like that, okay? But we just put the operators one after the other. But again, you should always read this from right to left, okay? So, and this is just a product of operators, but it means that it is a composition. Okay, so what is really pain in the neck in first quantization, so in the usual formalism, with the Slater determinants is that if you want to write them down on a piece of paper, okay, you basically have to write really a determinant, okay? And well, writing that determinant is just taking some time and it's not very interesting, but it's becoming really a nightmare if you have to actually do calculations, okay? So in second quantization, what's very nice is that if you want to create Slater determinants, so if you want to encode the Slater determinants, it's very simple. You just have to accumulate creation operators. So for example, if you want to, like you have, let's say, n spin orbitals, okay, P1, P2, 3, 4, up to Pn. So you selected these spin orbitals, and now you want to encode the Slater determinant. Well, in the second quantization formalism, the only thing you have to do is to start from this vacuum state and just multiply these creation operators. So here you see I created an electron in the spin orbital Pn, and then Pn minus 1, and so on up to A1. So it's encoded essentially exactly the same way as for two electrons. You just multiplied more creation operators, okay? So at first sight, it's very simple to write down like Slater determinants in second quantization. Okay, so this is the idea, this is the motivation, but if you actually want to derive anything, so if you want to, for example, be able to use that language to calculate many-body wave functions, you need some rules, because you understood that these creation operators are important, but actually you have somehow to drive them. You have to tell them there are things you have the right to do and some other things you don't have the right to do. So we need to give some rules which are like rules of the game. Once you know these rules, you can actually start working, okay? So, but this is important. So I will try to list these different rules. I will give them to you, and then we'll try to understand what they actually mean physically, okay? So these are known as the anti-commutation rules. So you will see later on why, okay? So, okay, so let's start. So for example, a simple question is, well, if you have two creation operators, okay? You may wonder, so does the order matter? So when I multiply two creation operators, does it matter if I write, for example, here, AP dagger, AQ dagger, or if I swap them, okay, like AQ dagger, AP dagger? So the first rule is, yes, it matters, because every time you will swap them, the two creation operators, you should have a sign minus that appears, okay? So if you change the label of P and Q, this minus sign should occur. Why? Well, this is, of course, connected to the first quantization. I remind you that second quantization is just another way to represent things, but it should be equivalent to first quantization. So why do we impose this, this rule? Well, if you apply these creation operators, for example, to the vacuum, okay, what you see here, because of this rule, is, for example, so again, I read from right to left. So I start with a vacuum. I create the first electron and put it in spin orbital Q, and then I create the second electron and put it in spin orbital P. Okay, So this is what's happening on the left-hand side. On the right-hand side, well, what happens is I start occupying the spin orbital P first, and then I put spin orbital Q. So we had already exactly this discussion in first quantization. What we said is, well, this is almost equivalent. The only difference is that there should be a minus sign. Well, that's exactly what happens. And this is why we need this rule, okay? So this is the first rule that the creation operators should fulfill, okay? And this is super important because one of the consequences is that if you consider the particular case where the two spin orbitals are identical, so if P is equal to Q, well, you can take this term then and move it to the left-hand side, and what you will get is that, well, basically, so this is what is at the bottom of the slide here, is when you start from the vacuum, so I'm in here, okay? So you start from the vacuum, you create an electron, put it in spin orbital P, and then you do exactly the same. So what happens, according to this anti-commutation rule here, automatically you get the zero vector, okay? And I mean really zero, not the vacuum, the zero vector, okay? So what does it mean? Well, it means that you cannot basically create two electrons and put them into the same spin orbital. And well, this is what we call the Pauli principle, okay? So this anti-commutation rule, so it's anti because you change the order, okay, and you get this minus sign, is just the mathematical translation of the fact that point number one, you cannot distinguish your electrons. Point number two, there is the Pauli principle, okay? So it has to be like that. So if you want second quantization to contain the same physics as first quantization, you need this anti-commutation. Okay, so at the moment we have the vacuum state, and we heard about the creation operators, okay? But of course, if you can create electrons, well, it would be nice if you could also actually annihilate electrons. So I mean, remove electrons, okay? To have really the complete picture. And so this is now what I'd like to tell you about. And so to understand where this is, where this concept of annihilation is, because it's actually already incorporated in the formalism, it's just that we didn't talk about it yet. We need to look a bit closer at these creation operators. So the important thing here is this Dagger symbol that I told you. Okay, we just call it Dagger, but of course you may have asked, why do we have this Dagger here? Is it important? Well, yes, actually it is. It means something, and this is what I would like to discuss now, okay? So, well, the first thing we can do is just look at it from a very like technical, mathematical point of view, which I'm going to do now. And then we'll try to understand what that means physically, okay? What is the physical meaning of this? So in mathematics, when you see a Dagger symbol like that, it means something. So it means that actually, if you write AP Dagger, it means that the quantum operator AP itself exists. And by taking the Dagger of it, it means that we are considering what we call the adjoint, okay? So if we were talking about matrices, the Dagger symbol, if we were using real algebra, would simply be the transpose of the matrix. So you have a matrix, AP, and then you take the transpose of it. That's essentially the idea, okay? So this Dagger symbol means something. So at least if you remain at the mathematical level, this is what we call the adjoint, okay? So what does it mean? Well, if you don't know what this is, it's actually simple. It's summarized in this equation here. So the concept of a joint appears when you try to move an operator from a bra to a ket, or from a ket to a bra. So this is what I'm describing here. So imagine you have this inner product here. So you have psi, the quantum state psi in the bra, and in the ket, what you have is the annihilation, that we will call later on the annihilation operator, but for the time being, it's just some quantum operator AP. So this quantum operator, you see, acts on the quantum state phi, and these two guys are part of the ket, okay? So in mathematics, when you want to move this operator from the ket to the bra, which then it's transformed into what we call its adjoint. So that's the general definition of the adjoint of some operator. Okay. So if you write epi Dagger, that we called the creation operator previously, it means that epi exists according to this mathematical definition. Okay, and you actually move from AP to its adjoint simply through this formula by moving from ket to bra. Okay? So this is just mathematical. Now, of course, the question is, okay, what is the physical meaning of this quantum operator AP? Okay, and well, it turns out that it will correspond to what we call an annihilation operator. But now I would like to explain you why. Okay, where does this come from? Okay, if we just rely on the mathematics, we should be able to understand why we call that some annihilation operator. Okay, so for that purpose, I propose you a little exercise that we are going to do together, step by step. So okay, let's start with that. So I will use, because the concept of a joint is actually coming from the calculation of inner products. We have to calculate some inner products and have this annihilation operator appearing so that we can understand actually what it means, why we call it annihilation operator, this AP operator. Okay. So what I'm going to do, I will consider the spin orbital phi p, which is just one of the spin orbital I consider. Okay. And so, you know, when I evaluate the square norm of it, I should get 1. This is something we discussed already in the first part of the lecture. Okay, so I will start on. Okay, and now, so this is just first quantization and nothing special. And now I'm going to translate that into the second quantization. Okay. So what I do is I consider that when actually I have this spin orbital, it means just that I have a quantum state where I have a single electron that occupies this spin orbital phi p. So now I just write this in terms of second quantization, okay, which is exactly what I do here. So how do I do that? Well, I start from the vacuum and I create an electron and put it in spin orbital. So this is really a first quantization way of writing things. This is a second quantization way, but they are completely equivalent, of course. Okay, and I do that in both the bra and the ket. All right, so just notation. Okay, and now I'm using, so this is the definition I gave you just previously about the adjoint. Okay, so what I'm going to do is I will simply take this creation operator and I will move it back to the bra. So if you really want to follow, I just wrote the notations with psi and phi so that you can use this formula. Okay, but basically I take that operator and I take it back to the ket, sorry. Okay, so if this happens, the creation operator will become an annihilation operator, which is exactly what I have here. Okay, so when it's moved from there to there, it became just annihilation operator. Okay. And so this is what I had. This is what I wanted. Okay, and I remind you, we started from 1, so this is still equal to 1. But 1, this is also the square norm of the vacuum state. Okay, so this came from the property of the vacuum state. All right, so if I just extract what I am interested in this formula, okay, is this. So these two things into the boxes are basically equal. Okay, this is what I can conclude now from this little manipulation. All right, so now I write this in a box here. So I just proved that when I evaluate, so the inner product of this quantum state with a vacuum, I basically exactly get the same thing as if I was just directly using the vacuum. All right, so at this level, this is just mathematics. Okay, now my question is, how can I understand this? And especially, what is the physical implication for this operator that I will call later on the annihilation operator? Well, again, I can basically, I need to read this equation from right to left to understand what's happening. Okay, so if I compare, so on the right hand side, what I have is just in the ket, I have the vacuum, okay, no electrons. And what do I have here on the left-hand side? So I have the vacuum, I created an electron, and then suddenly I'm doing something, okay? So I have this AP operator afterwards. And what I'm saying when I read this equation, somehow it's exactly the same thing as returning back to the vacuum. This is how I can understand this equation. So what does it mean? It means that basically I start from the vacuum, I create an electron, and then I go back to the vacuum. So what did I do? Well, I just removed that electron. And how did this happen? Well, I applied this AP operator. So what the AP operator does, it removes. So this is why it's called annihilation operator. So the annihilation operator, well, removes electrons, and it's a joint in the mathematical meaning. AP Dagger creates electrons, okay? So, and these are really the two building blocks in second quantization. So creation operators, AP Dagger, annihilation operators, AP, all right? And the connection, the mathematical connection between creation and annihilation is going through this joint property. So this is how mathematically the annihilation is connected to the creation of electrons. Okay. So this is the other beast. So basically, in second quantization, if you know the vacuum, I mean, you need the vacuum to start with. Now you can create electrons and you can annihilate electrons. So you can more or less do whatever you want. Okay. And this is how you're going to explore the entire Fock space, as I will show you later on. Because if you have the possibility to create electrons, you can have as many electrons as you want in your system, but you can also decide to decrease the number of electrons, okay? So you have full flexibility. And of course, if you can remove electrons and then create electrons, you can describe also excitations. And this is what I'm going to talk about later on, which is of course something extremely interesting for the description of the electronic structure. Okay, so because, yeah, of course, something important as a consequence of what I said is if now AP, the operator, the quantum operator AP is an annihilation operator, obviously, if it applies to the vacuum, there is nothing to remove, so you should get zero. And when I say zero, it's really the zero vector of the Hilbert space we use, which I call the Fock space, just to remind you. Okay, so this is an immediate consequence. Every time you will apply the annihilation operator to the vacuum, you will get zero. Okay, so that is something important. Okay, so now that I have introduced the annihilation operators, you may actually wonder, is there any anti-commutation rule? Because I talked about that for the creation operators. I remind you, this was connected to the Pauli principle. But what about actually the annihilation operators now? And well, actually, this is also mathematical, something just that is like immediately, you can prove immediately from the mathematics. So if you have the anti-commutation rule that is fulfilled by the creation operators, which I explained before, well, mathematically, you need to have also exactly the same property for the annihilation operators, just by taking the adjoint of this equality, okay? So it means that basically the same relation is fulfilled by the annihilation operators. So if you annihilate electron in spin orbital Q first and then P, it's almost the same up to a minus sign to remove the electron that is in spin orbital P first and then Q, okay? So if you swap two annihilation operators, you just have to remember to have a minus sign in front, and that's it, okay? So we have an anti-commutation rule when you have product of creation operators. You also have the same property when you have product of annihilation operators, okay? And well, and finally, of course, you may ask, okay, but what happens if I have let's say, a creation operator and then an annihilation operator, okay? And for that, of course, we need a last rule. I mean, one more rule. so that we can have a full, like we know what to do in case this situation actually happens, okay? And here is the rule. So this is actually the last rule that I need to show you, so that you can be fully operational. So so this is the anti-commutation rule that you see here on the slide, but this is now a rule that involves an annihilation operator and a creation operator. Okay. So what's different? Well, basically, you see this minus sign again. So when you swap the two operators, so AP, AQ dagger, and now you see you have AQ dagger AP, you still have this minus sign, exactly as we had before with the creation or annihilation operators. But there's something more here, you see. There is this Kronecker delta that appears. So that's the major difference, okay? So when you swap a creation and an annihilation operator, you need to verify if the two indices P and Q are the same or not. If they are not the same, you will just get the minus sign and that's it. If they are the same, you should have a 1, okay, in front. You have to be very careful. So this is a rule, okay? Now I guess I give it to you now. Of course, it's nice to understand what that means. So I will try to explain you where this rule comes from and how is it connected also to first quantization, okay? So, okay, so the rule is here. That's, I repeat, that's the rule of anti-commutation between creation and annihilation operators. And if I had to summarize this and give some kind of a physical meaning, well, I would write this, I don't know, this sounds like a Chinese proverb or something like that, but so you can only annihilate what has been created. So this is exactly, I think, the right way to translate this relation here, okay? Because that's exactly what it means, all right? So, so I will try to be a little bit more explicit about this. I will try to show you why I wrote this sentence, but it summarizes really what this equation actually means. All right, so so what I suggest is just to do a little exercise and yeah, to understand exactly why I use that quotation to summarize what this anti-commutation means. Okay, so imagine you start from a situation where you are in the vacuum, you create an electron and you put it in spin orbital Q, okay, and then you decide to remove an electron that occupies spin orbital P, okay. So we're going to see how you can transform this by using all the rules we have seen. So we are going to do this like step by step. And at the end, of course, we should get something that makes sense and that we can summarize with this sentence, okay? Okay, so let's do it step by step. Well, first of all, I will just use my, so this rule that is given to you, but we still don't know if it makes sense or not. So we want to check that, okay? So I just replace, you see, AP AQ dagger by delta PQ minus AQ dagger AP. So I simply replaced this expression here, okay? This is what I'm given. So I tell you, this is how it should be. And of course, you may wonder why. So that's what we're going to check, okay? To see if it makes sense. Okay, so now we have two terms, so we can split them. So you have the first term here with this delta P in front of the vacuum, okay? And then the second term you have, so the minus AQ dagger AP applied to the vacuum, which is what I wrote here, okay? All right, and then now I remember that when I apply some annihilation operator on the vacuum, there is nothing to remove, so I should get 0. So this guy disappears, and that's basically what's about, okay? All right, so how can I understand this? So if P differs from Q, of course, that will give me 0, okay? So, but that's exactly what I mean. Of course, if you create an electron, put it in spin orbital Q, and then you try to remove an electron in spin orbital Q, sorry, in P, but you never created that electron, of course, you will get 0. That doesn't make any sense, okay? So that's what I mean when I say that you can only annihilate what you have created first. So if you did not create the electron and put it in spin orbital p, you cannot remove it, okay? So that's what we learned from this formula. So that's definitely, it makes sense, okay? And so if I go back now, you see, if I now consider P equal Q, now I should get back to the vacuum. And that's exactly what the formula says. So if you start from the vacuum, create an electron in spin orbital P and remove that electron, okay, in the same spin orbital, well, then you're back to the vacuum. And that makes sense. So you have removed what you indeed created, okay? So you see that these commutation rules make sense. So when it's about the anti-commutation with two annihilation operators or creation operators, it's all about the fact that electrons cannot be distinguished. And also there is the Pauli principle, okay? If now we look at the anti-commutation rule between creation and annihilation operators, well, as I told you, it just means that you can only annihilate what you have created first. So all this makes sense. It's just that they are translated with this so-called anti-commutation rules. Okay, one last thing about this delta PQ here that is in this anti-commutation rule. I mentioned in the first part of the lecture, which was a review of first quantization, I told you that we were working with molecular spin orbitals that are orthonormal, okay? And so actually this delta PQ here is connected to that. So it was not very clear from the beginning, you probably didn't see it, but it is actually very important to keep this in mind that these rules of second quantization that I have discussed will only work if I'm working in a basis of spin orbitals that is orthonormal, okay? And I will show you that so that you keep that in mind, because if you were actually working in a non-orthonormal basis, your anti-commutation rules will not be that simple. And in particular, you would not have this delta PQ. So I remind you that the connector symbol here was appearing because we had an orthonormal basis, okay? And it's reappearing here in the notation of second quantization. But there is actually a connection between the two, okay? So so I can show you that. Also now another manipulation of these operators. So what I can do is start from what we have seen in first quantization. So if you take two spin orbitals and you evaluate the inner product between two spin orbitals, okay? So phi p and phi q. So in first quantization, I remind you, you would write this as an integral, but now we are moving on to second quantization. So I say, well, this is just like creating an electron and put it in spin orbital p, okay? And so this is what happens in the bra. And in the cat here, I create an electron and put it in spin orbital q. And now I can start playing with what we have learned previously. So for example, I can move this creation operator from the bra to the cat. So then the creation is becoming annihilation operator, as I explained. So this is exactly what happens. You see, when it moves from there to there, you only have the vacuum left in the bra. And here you have now the annihilation operator. And this part is unchanged, okay? Okay, now I can use again this anti-commutation rule between annihilation and creation operators that I talked about. So if I do this, I just replace that by what I have here, okay? So the first term is the delta PQ. So you see the delta PQ is coming from the anti-commutation rule here, okay? And then I have the square norm of the vacuum. I told you this is a quantum state that is normalized, so it's just one. And then you have the other part here. So minus the vacuum, and now creation, annihilation applied to the vacuum. And as I told you, you cannot remove anything that does not exist. So when you apply the annihilation operator to the vacuum, you get 0. So this guy disappears. So all in all, from the anti-commutation rule between creation and annihilation operators, you realize that, well, your basis of spin orbital must be orthonormal. It has to be, otherwise there is a problem, okay? So, so in summary, the fact that we have this connected delta here is connected to the fact that you are working in a basis of a normal spin orbitals. Okay, so it was a bit technical, probably, but I think, I mean, when you have the rules and you see, my message was really to show you how we manipulate this, because this is what you do all the time in second quantization. You spend your time moving creation or annihilation operators from Brad to Ketz and use this anti-commutation rule all the time to simplify things. So now you have at least an idea of how the machinery basically works. Okay. Okay. All right. So this is probably the most important slide of this presentation. I summarized on that slide what I think you should memorize to be ready to practice second quantization. Okay. So this, and I'm very serious, this is the only thing I need to know to actually practice. Okay, so of course now in the rest of this presentation I will show you how to use it and why it's useful. But okay, so what did we learn? We learned that we have a vacuum state, okay, and it is normalized. All right. We learned that we cannot, of course, remove something that does not exist. So every time you apply the annihilation operator into vacuum, you get the zero vector. We also learned that the annihilation operators anti-commute, so which means that AP, AQ plus AQ, AP is zero, and the same thing happens for the creation operators. And we know that this is the mathematical translation of the Pauli principle, okay? And finally, we also learned that there is an anti-commutation rule for annihilation and creation operators, okay? And the difference is that now we have this connected delta. So this means that you cannot remove what has not been created, but also this delta PQ here is immediately connected to the fact that you have an orthonormal basis of spin orbitals, okay? So if you ask me what should I know, this is what you should know, okay? So if you know this, you're ready to practice. So we have a question. So we don't have multiplied the wave functions by a normalization constant? No. No, exactly, Lucas. So that's the cool thing. That's a very good question. So if you, so now you can actually prove it yourself. Wait a minute. So if, yeah, so if you evaluate the square norm of this guy, you will immediately get 1 because of the anti-commutation rules. So the factor, 1 over square root of factorial n and so on, you don't need that anymore. Did I answer your question, Lucas? I guess. Okay. Yeah. Okay. Yeah. So this is, as I said, this is essentially the sum. Okay, so now that you know the formalism, so the language, let's just try to see how we can use it, of course, because there's no point in learning it if it's not very useful, but it is, you will see. So why do we learn this? And why do we want to learn how to encode a many-body wave function? Well, because at least in chemistry, you may want to solve the Schrödinger equation, okay? So DFT and other theories like green functions are beautiful because they try to bypass this task, but in chemistry, we can actually go for it. So the size of the system sometimes allows for it. So you can try really to design, to approach the exact wave functions. And this is where this formalism is quite powerful. Of course, it is also powerful in the other fields, I mean, in DFT, but also in green functions. But at least in this context, you will see it's very interesting to use the second quantized way of writing things. Okay, so how does it work? Well, in general, what we do, we expand the wave functions. Of course, we don't have access to the exact wave function, but we try to get as close as possible. So what we do, we create Slater determinants, and now you know how they are written in second quantization, okay? So I sum up over all kinds of spin orbitals because I can create all kinds of Slater determinants. Somehow I'm spreading my electrons over lots of spin orbitals, okay? And in front of each Slater determinant, I will have, of course, a coefficient that I need to determine, okay? So in the language of quantum chemistry, we call this configuration interaction expansion. So I have all this Slater determinant again, and I have this coefficient, okay? So I'm really using the Slater determinants as a basis. So the nice thing about the second quantization is that there is a kind of universal way of encoding such a wave function. And for that purpose, you can use the concept of excitations. So I will try to explain this. So usually, if you need to do like a configuration interaction calculation, whether it's exact or truncated, well, the question is, like, is there a smart way to generate all these Slater determinants? Okay, and yes, you can do that through excitation processes. So what do I mean by that? So imagine you do the Hartree-Fock calculation to start with, exactly as Vincent explained, okay? And what's going to happen is you're going to generate orbitals or spin orbitals. So some of them will be occupied, some of them will be what we call virtuals, so they will not be occupied. But you can use these unoccupied orbitals to generate more Slater determinants. So that's actually the idea of the configuration interaction. So in this simple example here, you see, I have, let's say, if I run, for example, Hartree-Fock, I picked up the two spin orbitals, and well, I just put my two electrons into these spin orbitals. So this will be what I will call my reference, okay? And in second quantization, it's written simply like that, okay? I have the vacuum, and I create the two electrons. So the first one in spin orbital 2 and in phi 2, and the second one in spin orbital phi 1, all right? Okay, all right. So, and now if I want to actually spread these two electrons over the entire spin orbital space, what I can say, so this is what I have, what you have here under your eyes is what I would have at the Hartree-Fock level. So these two spin orbitals are occupied and these guys are empty, okay? We usually call them the virtuals. So if I want to generate all possible Slater determinants, I can do that through excitation processes. So, so for example, I could say, well, for example, I will leave an electron in the spin orbital phi 1, and then I'm going to just excite. So take the electron that is in the spin orbital phi 2 and move it into the number 4, which is one of the virtual orbitals. Okay. So if I do this, I'm describing what I will call a single excitation process. So, so you see, I'm using the reference, let's say the Hartree-Fock as reference, and then I'm describing this new Slater determinant in terms of excitation. So starting from the reference, what I'm doing, I remove the electron that was in spin orbital 2, and now I put it with the creation operator in spin orbital phi 4. So annihilation and creation, then I'm doing a single excitation. I remove an electron somewhere and I put it in another. So with this creation annihilation operator, I can describe really a single excitation process, okay? Because a single electron has been excited, all right? But of course I can continue like that because I have like 2 electrons. So what I could also do is just excite from the 2 spin orbitals. So both electrons are now promoted to the virtuals, okay? And again, if I start from my reference, I apply, so I remove an electron in spin orbital phi 1 and put it in 4. This is what I'm describing here. And then I continue removing electron in spin orbital 2 and put it in spin orbital 3, okay? So, and now what I'm doing is a double excitation process. Of course, here I have only 2 electrons, so I cannot go beyond that, okay? There's no triple excitation, but if you have more electrons, you will have. So if I try to write this in a very general way, now going back to the problem, solving the Schrödinger equation. So what is kind of nice is that, of course, the reference in your calculation will depend on the system you look at, because the reference will not be the same for molecules that have different number of electrons. And even if they have the same number of electrons, of course, the orbitals might be different because they do not contain the same atoms. But what is kind of interesting is like through this excitation process, you have a kind of universal way, general way of describing basically a many-body wave function. So you always have a reference, okay? And you proceed by excitations to actually cover the entire Fock space, or at least a part of it, if you fix the number of electrons, okay? So basically, the reference is here. So the one is when you use that reference, let's say like Hartree-Fock as a starting point. And then, so as I explained for 2 electrons, you can proceed with like a single excitations. Then you can do double excitations. And if you have more electrons, okay, then you could have triples, quadruple, quintuples, and so on, okay? So rather than talking about the very specific number of electrons to have a very specific calculation, you can have a general theory where you talk about in very general way about singles, so the single excitations, the doubles, so double excitations, triples, and so on. This is how people derived, constructed very general quantum chemical methods, because they were more focusing on the type of excitations, okay, that they include in their calculations, rather than a very specific strategy for a very specific molecule. And all of this is encoded in a very simple way, as you can see in second quantizations, because it's all about explaining that an excitation just consists in like removing an electron and promoting it into another orbital. Okay, so second quantization is very convenient from that point of view. Of course, what has to be done there? Well, the job is to determine all these coefficients that we usually call the configuration interaction coefficients, okay? So I'm not gonna tell you about this, but that's exactly what you have to do when you want to actually model a many-body wave function, okay? And there are various ways to do that. Usually, of course, people truncate the excitations. So they decide to have like only the singles and doubles, or like, let's say the triples. You can use many-body perturbation theory to have approximations to these coefficients and all kind of methods that will be discussed next week, actually, okay? But what I think you can understand, nevertheless, is that what is basically happening. If you would like to find these coefficients exactly, what you would have to do is to diagonalize the Hamiltonian matrix in the basis of the determinants. That's essentially what you would have to do, okay? And if you want to do this, of course, you need to know how to write the Hamiltonian in second quantization, okay? Because I talked about the wave function here, but we didn't say anything about the Hamiltonian. And of course, if we don't know how the Hamiltonian is written in this formalism, well, there's no way we can do anything, okay? We cannot program, we cannot understand anything. So it's really important to know exactly how the Hamiltonian is written in second quantization. And okay, and that's what I'm going to do now. So, and I think this will be, once I'm done with that, I will be done with the second quantization. We have a question. Why is the bottom equation okay, very good question. Why is it an approximation? Because, okay, it would be exact if we had an infinite basis. So if we would cover the entire Hilbert space. But in practice, we always have a finite number of atomic orbitals. So the basis of spin orbitals is always finite. So which means that from the beginning, you will never have access to the exact solution. Is this okay, Shu Fei-Yong? Yeah, okay. Okay, so yeah, so now let's talk about the Hamiltonian, because this is, of course, a very important ingredient. I mean, if you want to solve the Schrödinger equation, you need to know how to write down this Hamiltonian. All right. So I need to start with the expression in first quantization, of course, which is the one you probably all know, and Vincent mentioned last week. So in the electronic Hamiltonian, so you have two contributions, what we call the one electron part, because this is like each electron individually will have its own like kinetic energy and an interaction with the nuclei, okay? And you sum up all this. So this is the one electron part. And of course, you have the complicated two electron part, yeah, okay? which contains the 2 electron repulsion. Okay. And the question is now how to write down the Hamiltonian in second quantization. So what I propose you, we're going to do a little exercise again. And so my question is the following. Let's just focus on the 1 electron part. Okay. And now let's just see how we can express this in terms of creation and annihilation operators. So it can be done, and I will try just to show you how it works, okay, where it comes from, so that you can have an idea of why we can actually do that, okay? All right. So, so first of all, when you run a quantum chemical calculation, so as Vincent mentioned last week, you need to calculate what we call the integrals, okay? Now I'm just focusing on the 1 electron part of the Hamiltonian. So the so-called 1 electron integrals. So H here is the 1 electron Hamiltonian, I remind you. So it contains like kinetic energy and the nuclear attraction. So, and these are the so-called 1 electron integrals, okay? So what you do with that? Well, you can actually construct the full matrix, the representation of the 1 electron Hamiltonian in the basis of the spin orbitals. And this is exactly what I did here, okay? All right, so what does this matrix mean, actually? Well, it means that if you stand, for example, in the column number R, okay, all these different elements here just tell you how the spin orbital phi R is transformed by the Hamiltonian. So this is how we read the matrix column by column, okay? And that's what I write here formally. So, so you have a summation over P because you sum up over all the rows of the matrix, okay? So that's how we read the matrix. And this is how I can actually find out about the way to write the 1 electron Hamiltonian in terms of creation and annihilation operators. Okay, so that's my starting point. So what I'm going to do now, I'm not sure, I mean, maybe it would take more time to go through the proof, but I will just try to convince you about each step separately. Okay, if you feel like everything is okay when we move from one equation to another, this is fine, and then you can go through that again by yourself. But at least I just want you to see that there is nothing tricky. With everything I told you previously, you can really follow in principle what is actually happening. Okay. All right, so so I repeat just to be sure, what I did here, I just used this column of the matrix, and I'm using the different matrix elements to tell you how one of the spin orbital is transformed by the Hamiltonian. And this is all I need to know, okay? And now I'm going to play around with that, and at the end, I will be able to tell you how to write the Hamiltonian in second quantization, okay? So we go for it. All right, so, well, step number 1, I just, so here I have, you see, a single summation over all the rows of my Hamiltonian matrix. And I introduce, you will understand later on why, a double summation. So I have summation over P, and here I have a double summation. I do nothing special. I just introduce this Kronecker delta here. So that when Q is equal to R, you go back here. Why do I do that? Maybe you see the trick. If I introduce this Kronecker delta, I can introduce the anti-commutation rule of second quantization, and then I can actually move on. So that's exactly what will happen. Okay. So so now I just write my spin orbital phi p in the second quantization way. I remind you, I'm just having the vacuum, and I create an electron in the spin orbital p. This is the way we write things in second quantization. Now I just do some rearranging. So I have, this is just a Kronecker delta, it's just a number. So I can just put my operator on the left-hand side. Okay, it costs nothing. Okay, but it's convenient, as you will see. So I do that. And now I'm using the anti-commutation rule that we have seen before. So I replace this Kronecker delta by this anti-commutator of annihilation creation plus creation annihilation. Okay, that comes from the rules of second quantization. All right. I also remember that when I apply the annihilation operator onto the vacuum, that makes 0. So which means that I can just remove that term. So that's what I do. Okay. And at the end, so this is what I have. Once I remove this, this term here. Now I go back to the first quantization way of writing things. So if I have a vacuum and creation operator, this is just my one electron state phi r. And finally, so at the end, I end up there. So what do I see? I see that through these steps, I was able to rewrite the Hamiltonian in a completely second quantized way. So which is into parentheses here, sorry, where you see that actually you have this double summation. So this is what I'm writing. So this is what is left. So if I have a single electron, basically I'm able to write the Hamiltonian fully with the creation and annihilation operators and the one electron integrals. Okay, so and what is nice, what I'm not showing here, but what is super cool is that this works for a single electron, as I just shown you, but actually it works over the entire Fock space. So in fact, this way of writing the Hamiltonian is valid whatever the number of electrons is. And actually you can see there's no information at all about the number of electrons in this expression. So it's super convenient because whatever the number of electrons is in your system, you can always use the same expression for the Hamiltonian operator, okay? So in first quantization, you would have to mention explicitly the number of electrons. Here you don't. The same expression is valid, okay? And of course, you need to know the one electron integrals if you want to run any calculation, okay? So you could do something similar for 2 electrons. I'm just showing you now the results so that we have the complete Hamiltonian. So this is what we had for the 1 electron part of the Hamiltonian. And now this is what we have for the 2 electron part of the Hamiltonian, okay? So, so I give you now the formula, but we can of course have a closer look at that. So how different is that from the 1 electron part? Well, first of all, you notice that in the 1 electron part, there's a single creation operator and a single annihilation. Okay? In the 2 electron part, you have instead 2 creation operators and 2 annihilation. This is actually, you can immediately know by looking at this expression if it's a 1 electron operator or 2 electron operator. So our colleagues in nuclear physics, when they try to model nucleons, you know, in the nucleus, they actually have also 3-body interactions, 4-body, even more, okay? So when they write the Hamiltonian in second quantization, you can immediately see if it's really a 1 electron, sorry, a 1 particle interaction, 2 particle, 3 particle. You just have to count the number of creation and annihilation operators, okay? So this is also a kind of thing, just by looking at the formula, you immediately know what kind of interaction operator you actually have in your Hamiltonian, okay? Okay, another thing, of course, is that now you see in front of this, like 2 creation and 2 annihilation operators, you have what we call the 2 electron integrals, which are important. So you have the 1 electron integrals, you also have the 2 electron integrals. So these are exactly the 2 electron integrals that Vincent introduced last week. So he used the chemist notation with the parentheses, and so I'm using more the physicist notation here, but it's exactly the same thing. I see we have a question. No, we don't. No, sorry. No. Okay. So what is that? It's exactly the same expression as the one that Vincent introduced last week. Okay. So now you have this double integral because it's a 2 electron integral. Okay. And so now you have the 2 spin orbitals in the bra with 2 spin orbitals in the ket, and now you have the 2 electron repulsion operator. Okay, so if you want to run a quantum chemical calculation, therefore, so you need to consider the full Hamiltonian, and it's now under your eyes. Okay, so there is the 1 electron part, the 2 electron part. You know all the rules about the creation and annihilation operators, so you can work now with your Hamiltonian, no problem. And if you want, so it means also that you can develop any theoretical method without having the numerical values of the integrals, okay? All the algebra you can do just from the anti-commutation rules and all properties of this creation and annihilation operators. So that's kind of nice. And of course, if you want to run a calculation on a computer, then you need to evaluate these integrals. So you will need the 1 electron integrals and the 2 electron integrals. So I used to say to my students, maybe for, so these are the kind of bones, the creation and annihilation operators are kind of bones of the Hamiltonian, and the integrals are like the flesh, okay? And then you get the full picture. Okay, so well, I'm basically done with the second quantization formulation, and so if you have to practice in the future, I think, as I said, I mean, you have now everything you should know. I mean, this is really the basics, but you see how basically the whole thing works. Yeah, there is an interesting question here. So I read the question. I see a great analogy between second quantization operators and ladder operators in harmonic oscillator problem. Yes, this is absolutely right. So the difference is that what you learned about the harmonic oscillator, you didn't have anti-commutation rule, you had commutation rules. And this works for bosonic particles. So the reason why we have anti-commutation is because we're talking about fermionic particles. That's the only difference. But if we were discussing about bosons, like if you work with the electromagnetic field, the quantum field theory, you would clearly have exactly the same properties. So is there something similar for breaking down second quantization operators in terms of some other operators in this method? I'm not sure I understand the second part of your question, Shima. Did I answer your question or? So the change of operators, it's like, for example, if you mean like change of basis set, this is something I'm going to talk about in the last part of the lecture. So I guess you can ask me your second part of your question or rephrase it later on if you want. Okay. 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 Yeah. So now I'd like to finish with the with actually a question that some of you have been probably thinking about for the last hour and a half, is like, why do you call this second quantization? Okay. All right. So okay. So I had my own opinion on that, and I checked just on the internet just to be on the safe side. So actually, this name comes from the old days, the early days. So it's a historical name that comes from the early days of quantum field theory. And as far as I've understood, actually, people in the field don't like it, this name second quantization at all, but it remained, okay? So we'll try to see exactly where it comes from. And then I will actually take this opportunity to introduce a couple of variables, like of quantities, which are very fundamental in various theories, like DFT, green functions, for example, okay? All right, so I think we're done now with technicalities. We are just going to rewrite things a bit differently. And yeah, and so as I said, I want just to explain where this name second quantization is coming from. Okay, so what I suggest is let's start from what we found just previously with this 1 electron Hamiltonian, but written in second quantization, okay? So I will take you by hand. So we'll do it step by step. What we're gonna do is just rewrite things a bit differently. And at the end, I guess you will see why this name second, okay? Okay, so I start from what we had. Okay, this, I remind you, this is the way we write 1 electron Hamiltonian in second quantization. What I'm doing now is I will rewrite explicitly what actually a 1 electron integral is. So it's just written there, okay? So you have integration, the orbital that is in the bra. Now you have exactly the 1 electron Hamiltonian and the spin orbital that is here in the cat. Okay. So it's just writing explicitly the integral. Okay, so now we can just do some manipulations. So for example, I decide to take the integration before the summations, why not? And So this is an operator, okay? This is just a number evaluated at some position. So I can actually change the order, there's no problem. And this guy does not depend on the position X. So I don't need to worry about this. So I just decide to move it here, okay? Why not? If I do this, I can write basically my Hamiltonian like that, okay? So this is just another way to write things. But there's something striking if you do this, actually, if you introduce a notation. So you see here on the right-hand side, you have this summation of all the spin orbitals. But this thing at the end depends on X. So I remind you, X stands for position and spin, okay? So if you denote, it's just a notation. We'll see later on why this is actually smart to do that. But if you just denote it like psi with a hat, because it's an operator, okay? The annihilation operator is an operator. So if you now make this summation, you create, you design or you construct an operator which depends, so that you evaluate at each position X. So this is what I do. So I will denote this operator psi hat of X, okay? So this operator is constructed for each position and spin in space. And if you do this, on the left-hand side, you have its adjoint that I just denote psi dagger of X, okay? So once you've done this, I repeat, this is just a notation. I didn't do anything, I just rewrote things differently, okay? But once you've done this, there's something funny that appears. So at the end, you Hamiltonian in second quantization looks like that. Okay? So what is kind of funny is if you remember what you learned from textbooks in quantum mechanics, when you evaluate for a single particle, the expectation value of the energy, so you have your 1 electron Hamiltonian. Well, this is exactly how it's written, okay? So of course, this is a number. It's an expectation value, so it's a real number, and it's written like that. What is kind of striking is now, if you move on to second quantization, okay, the Hamiltonian itself, which is an operator, is written exactly the same way. So, but now what has changed is that it looks like, it looks like if the wave function had been transformed into an operator. So in the single quantum theory, so in quantum theory for a single electron, you have a wave function, okay, which has some, so you evaluate at some position and spin, and that's in principle a complex number. And now when we move on to second quantization, the wave function, it looks like at least, has been transformed into an operator, psi hat of X. And this is what is called field operator. Okay, so as I said, this comes from the early days of quantum field theory. So in fact, in a quantum theory for a single particle, you have just a wave function. Now we have something that looks like a quantized version of quantum theory. So it looks like you made quantum something that was already quantum, okay? So this is where this name second quantization comes from. So I just remind you how this field operator is constructed. So by the way, what I forgot to say is that physically, so this guy is a kind of annihilation operator. So it removes an electron that would be at the position X with a spin X, okay, at position R and sigma. And this creation operator actually will create an electron and put it at position X. Okay. So this is just like creation annihilation operators in a different basis. Okay, so I see there is a question. So I believe you can write fermionic creation and annihilation operators in terms of Majorana operators, but perhaps there is a more general framework to decompose second quantization operators. Yeah, I'm sorry, I'm really not an expert in quantum field theory. About the connection between fermionic and bosonic, I know that there are some tricks in condensed matter physics that are used like to transform I think fermionic operators into bosonic ones, but I'm not an expert in that. There are some techniques that are used in electronic structure theory. Okay, so yeah, I can't say more, I'm sorry. Okay, so now that we have these field operators at hand, we can actually play with them. So, and that, I will finish with this because I wanted to make a kind of a connection with the lectures that will come after mine. Well, first of all, you know, in quantum theory of a single particle, the product of the complex conjugate of the wave function multiplied by the wave function, this is what we call the density of probability, okay? But now if you move on to second quantization, because the wave function is becoming an operator, well, you get what we call a density operator. So you have basically this operator, which, as I told you, removes an electron in position X, and then we put it back into an X. So it's the kind of way of scanning space. So is there an electron there? If yes, you get a non-zero result. If no, you get zero. So by doing that, you're actually evaluating the density, okay? But now it's funny that the density has become a quantum operator. So you may actually ask, how do we calculate the electronic density? Like, I mean, the number, okay? Because when you have many electrons, you can still evaluate an electronic density. How you do that? Well, if you have any many-body wave function that I denote here phi, so that there is no confusion with the field operators, okay? Well, if you want to evaluate an electronic density, the only thing you have to do, so if you want to evaluate it at point X, well, then you just take the expectation value of this density operator. This is exactly how you can evaluate, in principle, exactly electronic densities from a many-body wave function, okay? So, and the density, as you may know, is a basic variable in density functional theory, okay? So, and just if you're curious, if you do a highly accurate quantum chemistry calculation, and like people can produce very accurate densities, which is interesting to study some properties of DFT functionals, for example, they can actually evaluate this density, but then usually they return to the spin orbital basis. So this is exactly what I do here. So you see, I started to define the density with the field operators, but you can always go back to the spin orbital basis. So if you do this, so you see the dependence in the position now is inside the spin orbitals, the molecular spin orbitals that you have, okay? So I just replaced, again, the field operators by this expression. And now to evaluate the density, what you have to do, you have to evaluate these terms here. So you see, you start from your many-body wave function, you remove electron in spin orbital Q, and then you create the electron in spin orbital P. Well, this is what we call the one electron reduced density matrix. And it's expressed here in the basis of the spin orbitals. So when you do a post-Hartree-Fock calculation, if you can afford the evaluation of these density matrix elements, you can calculate ideally high accuracy electronic densities. Okay. So this is essentially how it works. So Pina Romagnolo will give a lecture about the one electron reduced density matrix theory later on, okay, in this school. So, but this is so that's one way to represent this density matrix, the so-called density matrix. Okay, you can also do it in space instead. So so I remind you, when you calculate a density, you remove and create electron exactly at the same point in space, but what you could actually do is consider two different points, like x1, x2, so two different positions, okay? And well, if you do this, then you get what we call the one electron reduced density matrix, but now it's written in real space, okay? So in fact, what we call the electronic density is just the diagonal of this density matrix. Okay. Yeah, and finally, because we are there to get the complete picture, until now I never talked about the time. Okay, I didn't say anything about time, but since we have these field operators, okay, you can actually make them time dependent if you want. So I talked about the field operator, this creation operator, you see. So until now, it was depending only on x1. So I remind you, x1 includes like position and spin, okay? So what is done in green function theory, actually, you transform this field operator into a time-dependent quantity. So how you do that? Well, you sandwich actually your field operator by this exponential IHT1 and minus IHT1. So T1 is the first time corresponding to the first position. And I here is the pure imaginary number, okay? So this is called the Heisenberg picture. So this is a way to make the field operator time dependent. And you can do exactly the same thing now if you introduce another time. And now you do it for the annihilation operator. And now, so if you, by analogy with what we have seen for the one electron density matrix, if you construct exactly the same quantity, so with this annihilation operator and then creation, but now including the time, what you do, well, you just created nothing but what people call the time-ordered green function. So, so these field operators actually are very important because this is where all the theory based on the so-called one electron green function starts. Okay. So I think I'm done basically. So at least I said what I wanted to say. So so I don't know if there are more questions or comments or, okay, I see a question. I have two questions, one related to this lecture and one related to the course. The first one is, are these the basic principles to include QED in quantum chemistry? No, not at all. So, so if you want to do QED in quantum chemistry, then you would need to, so now I'm just talking about the electrons, okay? If you want to do QED, you would need also to describe the photons in, with this second quantization, but that would correspond to bosonic operators. And then, of course, all these guys would, so you would describe basically the electromagnetic field with the quantized version of Maxwell equations. And then electrons and photons would interact in this global theory. And this is what we call quantum electrodynamics. But the formalism I'm talking about here is just for electrons. There's no photons whatsoever. I mean, the photons are treated implicitly, if you want, in the Hamiltonian through this, through the two electron interaction. If you were doing quantum electrodynamics, your system would be like photons and electrons. Here, I only have electrons, okay? So, of course, we can add QED corrections afterwards, but this is not what I'm talking about. But you would use the same formalism, but you need to complement it with the electromagnetic field treated quantum mechanically as well. Okay, I answered your question, Alberto. You said I have two questions, but I think I only answered one, so. So, okay, what form do the creation and annihilation operators have? I'm not sure whether you mentioned, okay, no, I didn't actually. So, I mean, you know, when you define operators, it's always a matter of representation. So, there is a basis where it's easy to define the operators. And then once they are defined in a basis, of course, you can change the basis and then the matrix representation will change. Why do I say that? Is because you see that you can define this creation and annihilation operators in Fock space in the basis of Slater determinants. This is the simplest thing to do. So for example, so let me see. Probably, how could I explain that? Oh yeah, yeah, exactly here. Oh yeah. So for example, you see, if I take this this what I was describing here, this simple simple example. For example, let's say you want to define the annihilation operator, and you do that in the basis, as I said, of the Slater determinant. So for example, if you apply the annihilation operator onto the vacuum, it's 0. So the vacuum would be the first vector of your basis. Then you would apply the annihilation operator onto this one electron state, and you know what it will give you, the vacuum. Then you could apply it to 2 electrons, Slater determinants, 3 electrons, 4, and so on. And you know exactly what's going to happen because you can use the anti-commutation rules. So in fact, the anti-commutation rules somehow define implicitly these creation and annihilation operators. And again, once they are defined in a basis, you can change the representation. There's no problem. So you know how they are defined. Okay, there is a question. Maybe I missed. What's the connection between field operator and wave function? Okay. That's a good question. So this is actually the reason why I think people in quantum field theory don't like this name second quantization. So you have to remember it's just an analogy. So the point is the following: is to say, okay, it's funny that these things look similar, but I mean we are not talking about the same thing. In this box here, I'm talking about an expectation value for a single electron. So this is a number, okay? Here I'm talking about an operator. So the point is to say that this is funny that somehow this is an expectation value for an energy. This is the Hamilton operator, but you can write them exactly the same way. So, but it looks as if you had transformed the wave function into an operator. But this is just a formal analogy, okay? Nothing more. And as far as I could understand from the literature, this brings some confusion sometimes because it looks as if the quantum theory of a single particle was not the quantum theory, but it is, of course. I mean, so, but here, this idea of calling it second quantization is just based on a formal analogy, nothing more. Is it okay? Okay. So I don't know if there are more questions or okay. The second question of Alberto is related to the fact that I'm new in taking online classes in all the universities. I'm sorry, but does yes, yes, Alberto, we can probably produce some certificates. Yes, but send me an email. It's easier then. Okay. All right. So if there are no more questions, I don't know, is it okay? Or so the lecture has been recorded and Francesco will put it on YouTube. So I will just put the link on the website and the lecture material as well. So you can really go visit the website regularly. I mean, we're not going to send an email all the time. You can just go there. You will see the list of slides and videos updated. Okay. So yeah, that's
exactly just the time of editing the video, and then we will put it.
Yeah. Okay. So you just have to be a little bit patient, but that should be fine. Okay. So I guess that's all. So thank you very much for staying with me this whole time, and yeah. And bye-bye. So see you next week.
Bye. Thank you very much, Emmanuel.
You're welcome.
Bye-bye.